Hello my friends and welcome back to the You Can Do TV channel.
The first roughing pass removes material using a depth of cut around 0.030 inches. Feed rate moves at approximately 0.025 inches per revolution. Combining depth of cut and feed rate determines how aggressively the tool removes metal during roughing. The tool advances along the programmed path, shaving the outer layer of the bar while maintaining the selected constant surface speed of 800. Each program line directs the tool position and cutting motion. The lathe adjusts spindle speed automatically to maintain the constant surface speed while the tool approaches the center of the workpiece. Constant surface speed allows the cutting edge to maintain a stable cutting condition along the entire diameter. Metal chips peel away from the rotating bar while the roughing cycle continues along the length of the part. Curl chips pile up quickly, looking almost like metallic ribbons forming beneath the tool. A small change in feed or tool position could alter the shape of the finished profile, which is why the hand program carefully defines each movement. Once the roughing pass is finished, the remaining shape appears clearly along the bar. Manual CNC code reveals exactly how every movement of the machine contributes to the final geometry. The operation demonstrates how traditional CNC hand programming still controls complex machining tasks through carefully written instructions. A CNC lathe can shape 12L14 steel entirely from manually written code without automatic programming software. Hand programming places full control of tool motion directly in the programmer's hands. A cylindrical bar of 12L14 steel is secured in the chuck of the CNC lathe. The machine references its coordinate system and prepares the cutting tool near the workpiece surface.
Notice how the milling head moves steadily across the roll surface. PROFIMILL portal milling machines handle massive workpieces, removing material layer by layer while maintaining strict dimensional control. Operators position each roll carefully on the machine bed, aligning it for consistent cutting paths. A surface that looks simple at the end hides countless controlled passes across the same metal. The milling head travels across the roll, gradually refining geometry without forcing the structure out of balance. HERKULES systems take over for roll machining, combining turning and grinding into a coordinated sequence. Each pass adjusts diameter and surface quality, preparing the roll for demanding industrial use. The transition between turning and grinding reveals how different forces shape the same material in stages. The roll keeps rotating steadily, almost like it refuses to show how much material is being removed. Grinding stages refine the surface further, smoothing out irregularities left from earlier machining. Texturing units introduce specific surface patterns depending on application requirements. Automation links each stage, transferring rolls between machines without interrupting workflow. Boring operations handle internal features, ensuring alignment across the entire roll body. Internal machining quietly supports the external finish, keeping the structure consistent from core to surface. One section gets refined, then another follows, and suddenly the entire piece reaches a uniform state without any obvious transition. The scale of these machines contrasts with the controlled movement of their tools, where every pass contributes to the final result. You might expect brute force to dominate here, yet most of the work depends on controlled contact and gradual removal. There's a moment where the surface changes from rough to smooth, and it almost feels like the metal settles into its final form. Cooling systems regulate heat during machining, maintaining stability across long operations. Temperature control prevents distortion that could accumulate over repeated machining cycles. Each machine handles a specific task, but none of them work in isolation. The sequence ties everything together. The roll moves between stages, and the transformation builds quietly with each pass. Measurement systems verify dimensions continuously, ensuring tolerances remain consistent. Seeing such heavy components treated with this level of control shifts how you think about large-scale machining. In the end, the finished roll reflects not just surface quality, but the accumulation of every controlled interaction across the entire process. Could a press line maintain this level of flow without constant human intervention? Pallets are scanned, blanks destacked, then centered before entering forming stations. Drawing presses shape panels, while robots transfer and reorient parts at the end of line. Panels flip and land exactly where they need to be, almost too clean for heavy metal work. Treating oversized parts like ordinary drilling jobs is the quickest way to overload tools, which is exactly why large part helical milling exists. Instead of attacking material in straight passes, the cutter advances along a controlled spiral path, gradually carving deep internal features inside an oversized workpiece. That spiral motion spreads cutting force more evenly, which directly reduces tool stress and improves dimensional stability. One miscalculated feed rate here would leave visible chatter marks across the bore, and nobody wants to scrap a component this size. The machine clamps the heavy part securely, aligns the spindle with programmed coordinates, then feeds the tool downward while rotating around the center axis in a steady helix. Material peels away layer by layer, forming long metallic ribbons that curl and fall aside. Compared with conventional drilling, helical milling lowers radial load and improves chip evacuation, especially in deep cavities. For oversized parts, this method isn't just an option. It's a reliability strategy. Tool engagement remains constant, minimizing sudden shock to the spindle. By the final pass, the bore diameter and wall finish meet tight tolerance requirements, proving why helical milling has become essential for large structural components. Combined forging, automated machining, PTFE seal extrusion, and synchronized assembly under one valve production structure. This unified framework aligns material flow, processing rhythm, and final integration within a single controlled chain. Forged bodies undergo impressing and tempering to reinforce structural strength before surface treatment improves corrosion resistance. Grain flow orientation remains consistent through controlled deformation sequences. Keeping accessory production internal stabilizes supply and prevents variation in critical parts. No external outsourcing interrupts dimensional consistency. Machining automatic special machines equipped with manipulators and servo motors perform dual-stage operations using profile cutters. Servo-driven indexing maintains positional repeatability across continuous cycles. Rough castings convert into semi-finished components through coordinated processing. Stable cutter paths reduce dimensional deviation across large production volumes. Tool engagement angles remain optimized across varying material densities. Output increases without compromising uniformity. Ball automatic special machines complete key dimensions in a single cycle, replacing former multi-step handling. Single cycle completion reduces transitional error accumulation. Reduced clamping transfers lower alignment shift and surface damage. Diamond cutting tools deliver raw 0.8 surface smoothness, sustaining sealing performance beyond 10,000 operational cycles. Surface integrity remains stable under repeated pressure fluctuation. That life cycle benchmark directly strengthens product credibility in demanding systems. Valve rod automatic special machines refine copper bars into finished rods through integrated processing, reducing efficiency loss associated with older equipment layouts. Continuous feed mechanisms maintain dimensional stability throughout rod length. PTFE seal ring special machines apply one-step extrusion molding. Extrusion pressure control ensures homogeneous density distribution within each seal ring. Independent seal production protects pressure integrity and eliminates inconsistent third-party materials. Procurement channels remain tightly controlled to secure raw material stability. Material verification protocols operate at each intake stage. Full automatic assembly lines incorporate infrared inspection and synchronized assembly control. Assembly timing sequences remain digitally coordinated across all stations. Labor shifts towards supervision and system management rather than repetitive handling. General interworking between equipment platforms increases throughput while lowering operational strain. Continuous technical upgrading reinforces reliability across the entire valve manufacturing chain. Hold a metal cutting axe and ask what gives it the nerve to survive impact. The answer lies beneath a 3x-ton hammer shaping 4H5 MFS steel. The steel reaches forging temperature and glows evenly before moving into alignment beneath the ram. Uniform heat at this stage allows the internal structure to deform without tearing. The first strike compresses the billet vertically, forcing material to spread laterally and establish the core mass of the axe body. The operator rotates the workpiece between blows to maintain symmetry. Each downward impact refines thickness while extending length toward the future blade. The hammer descends again and again, compacting the steel and eliminating internal voids. Repeated compression drives density deeper into the core, not just along the surface. 3 tons of force do not just shape the surface, they penetrate through the cross-section. Scale flakes off with every strike as the profile becomes more defined. Angled strikes begin drawing out the blade edge. Material shifts forward, concentrating mass where cutting strength is required. Shift the billet a few millimeters off center, and balance would suffer immediately. Careful repositioning keeps the geometry true while the eye section starts forming through localized upsetting. Controlled sequences of compression, drawing, and upsetting gradually reveal the recognizable axe silhouette. By the final forging passes, thickness distribution matches functional demand, reinforced around the eye, tapered toward the edge. At this point, the steel no longer resembles a billet. It carries the unmistakable presence of a working tool. A properly forged 4H5 MFS AX gains its durability right here under the 3x ton hammer. Every strike contributes directly to structural integrity before the piece ever leaves the anvil. Move heated steel through sequential dies on the Becce 16 line and shape it under EUMUCOR-W2 force. Ed-hot steel blanks move onto the transfer system, guided between forming stations in a fixed sequence. Automation here is not decoration. It directly stabilizes output and timing. The EUMUCOR-W2 unit delivers the primary forming force, shaping each billet through successive dies that gradually refine geometry. Mechanical grippers reposition the workpiece between strikes, maintaining alignment under heavy load. Each transfer must sync perfectly, or the entire cycle loses efficiency. Temperature control remains critical, so induction heating keeps material within the required forming range before deformation. After forging, trimming presses remove excess flash and parts advance toward cooling and inspection. Dimensional checks confirm tolerances before components move to downstream machining. Everything links together like a chain that cannot afford slack. One missed beat would throw off the whole line. High-speed engine rotation depends on a forged crankshaft shaped under heat and force, and this forging process proves that skill still anchors modern manufacturing. Steel bars enter the furnace and rise to forming temperature before moving to the forging station. Strength is built through controlled impact, not just raw pressure. Under repeated hammering, the glowing billet spreads within shaped dies, gradually forming the crankshaft profile. A free hammer unit remains part of training, allowing operators to practice manual strikes. At first, new trainees struggle to control timing, alignment, and force. Wow, progress does not come quickly here. Lubrication technique, tong grip, material orientation, and subtle adjustments based on temperature and humidity all influence the result. Experience fills the gaps that numbers cannot describe. Repetition builds consistency until the trainee can complete a die forging alone. That moment carries real satisfaction. Later, refined human techniques transfer into automated systems. Machines handle volume production, yet they rely on instructions shaped by skilled workers. Behind every mass-produced crankshaft stands learned judgment and steady hands. High automation and tight dimensional control operate side by side in this duct production process. Steel sheets are lifted from stacks through destacking units equipped with double sheet control to prevent feeding errors. Stable input at this stage protects everything that follows. Edge preparation refines both sides of each blank before it enters the forming section. Blank infeed systems position material for manifold production, whether two-fold or four-fold configurations are required. Configuration flexibility allows the same line to handle multiple duct geometries without rebuilding the setup. Next, Two-roll round bending curves the sheet into a cylindrical profile. The joint edges align under a laser welding head powered by a Trumpf laser source, fusing the seam with concentrated energy. Oh, that transition from flat sheet to closed tube happens fast. Seam planishing smooths the weld bead, ensuring uniform thickness along the joint. Annealing follows to relieve internal stresses introduced during forming and welding. Calibrating stations adjust final dimensions, holding tight tolerances for round, oval, or rectangular output. Expanding units complete shaping by slightly enlarging the tube to exact specification. Each stage reinforces structural consistency, while keeping production fully automated. By the time the duct exits the line, forming, welding, heat treatment, and dimensional correction have already been integrated into one streamlined sequence. Coordinated sequence with a fully automatic line, built to process heavy profiles without manual repositioning. One uninterrupted chain handles tasks that once required separate crews and separate setups. An automatic loading system feeds raw edge beams and channels onto roller conveyors, guiding each member toward the first station. Continuous flow eliminates repeated handling, which directly improves throughput. Less lifting, less waiting, more steel moving forward. Without halting the line. A single profile can carry dozens of holes within minutes. Accurate hole placement determines how smoothly the structure assembles later on site. If those holes drift off target, installation crews pay the price later. After drilling, the beam advances through buffer zones that separate each machine. These zones maintain spacing, preventing interference while keeping production uninterrupted. The sawing station follows, putting the steel member to exact length based on visual input. Cut length accuracy prevents alignment issues during final construction. Millimeters matter here, especially once beams meet columns hundreds of feet above ground. Next, the coping unit shapes beam ends to fit connection joints. Material is immersed in controlled cutting paths that match structural design requirements. Automatic unloading systems then transfer finished members to output racks. No manual flipping, no chain slings swinging across the aisle. Every section remains isolated, yet digitally linked, forming a multi-channel workflow that balances speed and control. Automation here does not replace oversight. It embeds it into every program. CNC becomes the flying advantage shift after shift. That integration keeps structural steel production consistent across long shifts. A single press cycle determines whether a stainless steel sheet becomes a durable cooking pan or warped scrap, and this hydraulic press drives that decision across the stainless steel pan production line. Flat sheets are positioned beneath the upper die, secured before any motion occurs. A bimanual console requires concurrent activation, backed by a Category 4 emergency stop. No dual signal, no movement. Stroke distance is adjusted through a manual override panel, while an inductive sensor refines travel depth. Pressure responds to a calibrated pressure switch to match medium or heavy stamping requirements. Once parameters align, the ram descends and forms the pan body in a single controlled action. Textured epoxy paint protects the surface against wear in continuous operation. A mechanical interlock hammer reinforces safety throughout each descent. Optional PLC with HMI allows position and pressure transducers to be adjusted directly on screen. A digital counter records each completed pan for production tracking. Red-hot billets shrink in diameter again and again until reinforced steel bars emerge from a 4-operator rolling mill line. Heated stock feeds into the first stand, where rotating rolls compress and extend its length while narrowing diameter. Each squeeze forces the metal to reorganize deep inside the core. Subsequent stands continue calibrated gap adjustments to reach target gauge. Cooling beds regulate heat release for structural stability. That blazing strand ends up ready to support entire skylines. Seriously powerful. Straightening and cutting units finalize length before stacking. A shipyard apprenticeship for shipbuilding metal fabrication shapes future construction mechanics through hands-on vessel production training. Trainees step onto full-scale hull sections and begin learning plate alignment, tack welding, and structural assembly. Steel panels only fit correctly if measurements are respected down to the last mark. Under instructor guidance, they operate cutting torches and forming tools to prepare bulkheads and frames. Suddenly, the scale of real ship structures hits hard. Graduates leave qualified for complex ship structure fabrication. High-speed automotive production depends on something that almost looks slow: controlled sheet separation on a front-of-line destacker for C-class automotive parts. Pallets arrive by forklift, placing multiple blank stacks under laser guidance for accurate positioning. Automatic indexing advances each stack into the separation zone. Active separation lifts single blanks while double blank detection scans during movement. An optical line scanner checks blank position continuously. The integrated feeder unit corrects offset before transfer to the press. A shuttle system moves sheets forward at high speed without compromising stability. Dual magazines keep material available while new stacks are loaded. Tooling change engages across connected machines simultaneously. Master booms, fitted with compact tooling arms, support ergonomic adjustments. Output reaches 25 strokes per minute with consistent front-end preparation.
A thin steel wire appears flexible, but the wire nail making machine turns it into rigid construction nails. Each nail begins as straight wire fed into the forming unit. Rollers guide the wire forward while the cutting die slices exact nail lengths. That quick cut already decides the nail size used later in construction. The machine presses one end to form the nail head, while the opposite side moves into the sharpening section. One push shapes the head, another strike forms the point. Wow, such a tiny object comes from serious mechanical force. Finished nails drop into the collection tray ready for packaging. Would you expect a simple metal cylinder on a lathe to transform into a complex threaded turning part through a few guided cuts. The complex threaded turning part forms through a sequence of controlled passes on the lathe. The chuck holds the workpiece steady while the machine brings the cutting tool toward the surface. Every adjustment here determines the geometry of the final thread. The first passes remove excess metal along the outer diameter. Straight sections appear gradually while the tool advances along the axis. One steady feed can reshape an entire length of metal in seconds. The surface becomes smoother after each controlled cut. Next comes the thread cutting stage. The tool moves in synchronized steps with the rotating spindle, carving a spiral groove along the shaft. A single misalignment would distort the entire thread path, so the setup must match the rotation perfectly. Pass after pass deepens the thread profile until the grooves reach their final dimensions. Additional turning steps refine shoulders, narrow sections, and transitions along the part. Those tiny ridges disappearing along the surface show how much metal has already been removed. The shape becomes more complex as the tool shifts position across different areas of the workpiece. A finishing pass then smooths the remaining surfaces. Edges appear sharp and the threaded section aligns cleanly along the shaft. Metal chips scatter around the tool. Suddenly, the rough blank looks like a finished mechanical component. The completed complex threaded turning part leaves the lathe ready for assembly in larger mechanical systems. Feed the heated billet into the rollers, and this production process stretches it into long reinforcement bars. The bar production process transforms heated billets into reinforced steel bars used in construction. Rectangular billets enter a reheating furnace, where temperature rises high enough to soften the metal for rolling. Without this stage, the steel would resist deformation, so heat prepares the billet for the heavy shaping ahead. The hot billet then travels into the rolling mill. A sequence of rollers compresses and elongates the glowing steel, gradually forming the long bar profile. Each pass through the rollers reduces thickness and increases length. A single billet stretches dramatically along the mill line. Metal that once looked compact now runs several meters farther. Rib patterns appear along the bar surface during the later rolling passes. These raised ribs improve bonding between steel reinforcement and concrete structures. Those small ridges decide whether the bar grips firmly inside a building frame. Immediately after rolling, the bar passes through a rapid cooling stage. Water jets surround the hot steel, lowering the surface temperature while the inner core remains hotter. This temperature contrast creates the strong outer layer that gives TMT bars their durability. The bars continue moving along the runout table until they reach cutting equipment. Long lengths are trimmed into standard sections ready for transport. Glowing metal enters one end of the line, and organized steel reinforcement emerges at the other. A turbine blade leaving the milling station already looks finished. The toughest metal shaping happened minutes earlier under ceramic cutters. A turbine blade blank locks firmly in the clamping system while a ceramic milling cutter approaches the airfoil surface. The cutter runs close to 1,000 meters per minute cutting speed, while the spindle rotates around 5,063 revolutions per minute, forcing the inconel alloy to give way layer by layer. This cutting speed alone separates ceramic tools from ordinary carbide cutters. The milling body carries round ceramic inserts that spread load along the edge and reduce cutting force during contact with the alloy. Material disappears quickly as the tool advances along the curved blade profile. Table feed moves near 2,728 millimeters per minute, pushing the cutter through the profile and face milling zones. Metal that once required several cautious passes now clears in a much shorter machining cycle. Air coolant channels direct airflow through the cutting area to guide chips away from the insert edges and maintain tool life. Profile milling defines the airfoil geometry, while face milling stabilizes the blade root. The blade gradually reveals its final aerodynamic form, shaped entirely under the pressure of ceramic cutting edges. A titanium aerospace component only half a millimeter thick can still survive aggressive 5-axis machining. Rough machining uses an 80 millimeter milling tool at 60 meters per minute cutting speed with 0.8 millimeter feed per tooth. Titanium resists every pass like stubborn armor. Finishing follows with the same 80 millimeter tool running near 100 meters per minute and 0.13 millimeter feed, refining walls down to 0.5 to 2 millimeters. A finished leaf spring appears ready for installation. The load testing press often reveals whether it actually meets the required strength. Steel finally tells the truth. Industrial foundry casting stands among the few manufacturing methods where liquid metal directly forms machine parts. Molten metal leaves the furnace and enters sand molds shaped for mechanical components. The cavity inside each mold already carries the final part's dimensions. Workers tilt the ladle and guide the metal stream into several mold gates. The liquid metal spreads through internal channels and fills the cavities. One bright pour suddenly decides the entire form of the casting. Wow! That moment changes everything. After solidification, the sand mold is broken open to remove the raw metal piece. Fresh castings appear rough and gritty, almost like metal pulled straight from buried stone. Large engine parts reach CNC milling only after the VERICUT system verifies machining paths digitally. Toolpaths undergo digital verification first. Unexpected collisions avoided, seriously reassuring. CNC milling follows validated programs.
Two 5 OMW hydropower generators regain full strength here through stator and rotor rehabilitation. Generator Services Workshop handles pole cores, straight and trapezoidal coils, diagnostics, and certified upgrades. This scale of restoration truly stands out. Snap under load, and a towing rope can turn a routine mooring operation into a life-threatening emergency. This breakdown focuses on how to splice mooring lines and prepare a towing rope correctly. A properly braided rope holds enormous tension without unraveling, which is critical during ship-to-ship mooring at sea. One weak splice can shift the entire load to neighboring lines in seconds. That sudden redistribution multiplies force instantly, and failure spreads fast. No captain wants to repeat a 4-hour setup because of one loose end. The rope is first inspected along its full length to check fiber condition and hidden damage. Next, strands are separated evenly at the working end to prepare for interweaving. Each strand passes alternately over and under opposing strands, forming a tight back splice that locks tension into the rope structure. Pulling each strand snug at this stage directly increases holding strength. The weave continues for several rotations until the tail is fully secured. Excess fiber is trimmed cleanly to prevent snagging during deployment. For towing applications, the I-splice must form a balanced loop size to fit shackles or bollards. Equal strand tension around the loop prevents distortion under load. During mooring at sea, stability depends entirely on these connections. A correctly spliced rope doesn't just hold, it protects crews and vessels from cascading failure. Under extreme strain, ropes can recoil violently if they part, and nobody standing nearby forgets that sight. Proper splicing transforms a simple rope into a dependable lifeline. Even compact hydraulic mechanisms can shape billets heavier than a person could lift. A 150 by 150 and 180 by 180 millimeters hydraulic billet shear controls heavy metal billets with surprising authority. Even the thickest billet obeys the shear's force with minimal deflection. The triple gearbox coordinates movement, distributing power evenly across the cutting span. Stands and combined gearboxes stabilize the operation, ensuring a clean cut each cycle. Rollers guide the billets smoothly. Automatic length cutting shears can handle billets sequentially, optimizing throughput. Couplings and flywheels synchronize motion, reducing strain and vibration. Guided platforms keep billets perfectly aligned before cutting. Every element, from hydraulic cylinders to mechanical supports, works in harmony to maintain precision and efficiency.
Which engineering stages bring an ENER-CON wind turbine from steel plates and composites to a full electricity producing system? Turbine manufacturing, installation, commissioning, and long-term service all connect to keep the generator producing energy. Electric power here comes from air movement, yet the engineering behind that idea runs deep. Production of an ENER-CON wind turbine begins with tower sections fabricated from heavy steel plates. Rolling machines curve the plates into cylinders, then welding units join the seams to create tall tower segments. Each section must align perfectly so the tower carries the turbine weight safely. Coating lines add protective layers against weather exposure. Nacelle assembly follows with the installation of the generator, hub interface, and internal drive components. The generator design removes the need for a conventional gearbox, reducing mechanical complexity. That detail alone changes how maintenance teams approach the turbine over its operating life. Rotor blade manufacturing forms the next stage. Composite materials are laid into large molds and cured to create long aerodynamic blades. A single blade stretches longer than many passenger aircraft wings. Quite a scale jump for a structure built from layered materials. Transport brings tower segments, nacelle, and blades to the wind farm site. Cranes lift each tower section into position, stacking them vertically before the nacelle mounts on top. Rotor blades attach to the hub and complete the turbine structure. One moment the site holds scattered components. The next moment a full turbine stands over the landscape. Commissioning technicians connect electrical systems and control units, preparing the turbine for grid operation. Monitoring systems track wind conditions, rotor speed, and power output during operation. Continuous data analysis keeps the turbine performing reliably through changing weather. Large CNC machining centers, such as the DMU 600G milling machine, combine heavy frames, drive systems, and electronics during assembly. Rigid base alignment secures machining stability. Final calibration prepares the machine for operation. A compact turbine wheel powers hydropower stations. The Pelton runner behind that motion involves demanding metal machining. Steel blocks move into machining centers, where the runner hub receives its circular geometry. Solid metal gradually revealing a turbine shape already hints at the power it will later control. Separate bucket components take form through milling and surface shaping. Each bucket carries the curved splitter that divides the incoming jet of water. That tiny ridge in the center decides how efficiently water energy transfers into rotation. Buckets move to assembly, where technicians mount them evenly around the runner hub. Final surface finishing smooths contact areas exposed to high-velocity water jets. Picture a water jet striking those buckets at full force. Suddenly, the structure feels alive. Laser cutting may appear suited only for thin sheets. The 6 kilowatts fiber laser metal cutting machine handles thick copper, brass, aluminum, and steel plates. Thin 3 mm copper plates pass under the laser head, where concentrated light traces programmed lines. Copper reflects energy strongly, so stable beam control matters during this stage. Thicker 6 mm copper follows, and the cutting head adjusts speed and power to maintain a clean curve. A narrow beam carrying several kilowatts of energy changes how thick metal plates respond to cutting forces. Stainless steel plates move next. 14 mm stainless material sits firmly while the laser head travels across the programmed path. That bright cutting line shows intense heat localized into a tiny zone rather than spreading across the sheet. Brass plates then enter the cutting area. Material thickness increases gradually from 15 mm to 18 mm and later reaches 20 mm. Each pass requires parameter adjustments for power level, assist gas pressure, and travel speed. Those settings determine how smoothly molten metal exits the cut channel. Aluminum plates appear afterward. 20mm aluminum sections slide across the cutting bed under the laser head. Aluminum conducts heat quickly, so beam stability and gas flow guide the cut through the plate. Larger 25mm aluminum panels follow, demanding slower motion and stronger assist gas flow. A glowing slit races across thick steel faster than many mechanical cutters could manage. Seriously unexpected speed. Clean-cut surfaces and consistent kerf width confirm that the 6 kilowatts fiber laser metal cutting machine handled copper, stainless steel, brass, aluminum, and mild steel across multiple thickness levels. Heated steel leaves the furnace and enters the forging press. What change inside the metal makes the future tool survive heavy torque? Heated steel bars move toward forging presses that compress the metal into wrench and socket shapes. The newly formed pieces travel to trimming stations where excess edges are removed. Milling machines then cut drive openings and contact surfaces used during mechanical work. Heat treatment follows to increase hardness and durability. The tools pass through grinding and surface finishing that refine edges and working faces. A simple wrench now carries the strength built through several demanding steps.
Steelmaking is often mistaken for simple melting, overlooking refining, and rolling stages that define final strength. Crushed and screened ore enters the furnace for high temperature reduction, separating iron from oxygen. The resulting molten iron moves to refining units, where carbon levels are adjusted and impurities removed to meet required steel grades. Chemical balance at this point determines strength and durability later on. Liquid steel flows into continuous casting machines, forming slabs or billets that solidify under controlled cooling. Rolling mills then compress and extend these semi-finished forms into plates, bars, or coils. Under heavy force, glowing steel stretches like soft clay, only at temperatures that demand serious respect. Controlled cooling stabilizes the internal grain structure before further processing. Heat treatment improves mechanical properties, while surface finishing enhances corrosion resistance and dimensional accuracy. Final inspection checks composition, thickness, straightness, and structural performance. Each verification step locks in reliability before the steel leaves the line. Seeing raw ore evolve into engineered steel products delivers a sharp reminder of how industrial metallurgy reshapes basic earth materials into load-bearing structures.
Old circuit boards look like waste, but inside them remain valuable copper and precious metals waiting for recovery. Electronic waste arrives as mixed components containing wires, circuit boards, and connectors. Recovering metals from this material prevents large amounts of valuable resources from disappearing into landfill. The incoming scrap passes through shredding equipment that reduces devices into smaller fragments. Metal pieces, plastic parts, and circuit board materials break apart during this stage. Shredding exposes internal metal layers so later separation systems can isolate them more effectively. Magnetic and density-based separation equipment then divides ferrous metals, non-ferrous metals, and lighter materials. Copper-rich fractions move toward refining steps. Different separation techniques isolate copper, precious metals, and remaining materials into distinct streams. Further processing extracts copper, along with smaller quantities of gold and silver contained in electronic components. A single pile of discarded electronics quietly contains several valuable metals waiting to be recovered. Recycling systems transform complex electronic waste into reusable metal resources, ready for new industrial production. The small ratchet head on the workbench hides the part that actually decides whether a bolt tightens or slips. Forged steel blanks form the foundation of the ratchet body. Heated alloy steel is pressed in forging dies to create the handle and the rounded ratchet head shape. Excess material from the forging stage is trimmed away, so the part matches the final outline of the tool. Forging compacts the steel structure, allowing the ratchet body to withstand repeated torque during mechanical work. Machining equipment then cuts the internal cavity in the ratchet head, along with the opening for the drive square. Channels for the selector switch and seats for the internal components are also formed during this stage. Accurate machining ensures the internal parts fit tightly and transfer torque without slipping. Separate steel pieces for the drive square, gear mechanism, springs, and locking parts are manufactured through precision machining. These parts receive heat treatment to increase hardness and wear resistance. Hardening allows the mechanism to handle thousands of tightening cycles without rapid wear. Surface polishing prepares the ratchet body for chrome plating. The plated finish protects the steel from corrosion while producing the bright reflective surface visible on the finished tool. The coating also reduces surface wear during constant handling in mechanical work. Assembly workers place the internal mechanism into the ratchet head. The drive square, gear system, springs, and retaining rings are installed in sequence. A small selector lever is inserted to control the rotation direction. A handful of compact parts suddenly turns the forged steel body into a functional ratchet. Completed ratchets are arranged in rows for inspection and packaging before entering toolboxes used in mechanical work. A coil of copper tubing in an HVAC system hides a long chain of metal-forming steps behind its smooth surface. Refined copper first enters a melting furnace and forms billets prepared for continuous processing. The billets pass through hot extrusion that pushes solid copper into long hollow shapes. After cooling, multiple drawing stages reduce the diameter and extend the tube length. The metal stretches farther than most people expect from a solid bar. Annealing restores ductility, then straightening and inspection complete the copper tubes used for fluid transfer and refrigeration. From outside, the bandsaw blade may look aligned already, but the RWA teeth setter still corrects each tooth before real cutting begins. The blade enters the automatic RWA teeth setter, where each tooth passes under a calibrated pressing head. Zeroing keeps tooth spacing uniform across the blade. One crooked tooth could send a whole cut drifting sideways. Detailed metal parts used in machinery often trace their origins to the investment casting WA melting process. Many parts produced through this method appear finished straight from the mold, yet a long chain of preparation happens earlier. Tiny wax patterns quietly determine the geometry of the final metal part. Production moves forward with wax injected into metal molds that form exact replicas of the future component. Each wax piece connects to a central sprue, creating a cluster often called a tree. One tree can carry many parts at once, turning a small wax model into an efficient casting batch. Workers dip the wax assembly into ceramic slurry, then coat it with fine refractory sand. The layer dries before the assembly returns for another dip. Several cycles gradually build a rigid ceramic shell around the wax patterns. The shell becomes strong enough to hold molten metal without collapsing. Heating the shell melts and drains the wax out, leaving hollow cavities inside the ceramic structure. This moment always surprises new viewers. Solid shapes vanish and perfect casting spaces remain. The empty shell then moves into a furnace for firing, strengthening the ceramic and removing residue. Molten alloy enters the heated shell through the central channel. Metal fills every cavity formed by the earlier wax patterns. Cooling solidifies the metal components inside the shell. Breaking the ceramic shell reveals the metal cluster. Individual parts are cut from the central sprue and move through grinding and finishing. Edges sharpen, surfaces smooth out, and the original wax geometry finally appears in metal form. Finished investment cast components are ready for demanding mechanical applications where detailed shapes and consistent strength matter. Components weighing from a few kilograms to extremely large structures can be machined on the SORALUCE Multifunction Machining Center. One setup handles milling, boring, and drilling. Huge parts suddenly look manageable here. What kind of system turns molten steel into thin industrial coils? Scrap, iron ore, lime, and fluxes enter the converter, while a thermodynamic model calculates chemical balance. Digital calculations quietly guide the furnace decisions behind the scenes. Infrared cameras supervise vessel tilt for bulk alloy additions that stabilize the molten bath. Temperature checks arrive through an auto lance. Numbers shift constantly while the steel chemistry settles into target range. Continuous casting follows, producing slabs about 55 to 70 millimeters thick and up to 1,700 millimeters wide. A mold-level controller using COB ALT60 and scintillation monitoring maintains metal height. Radioactive measurement equipment sounds dramatic, yet here it simply keeps the steel flow steady. Slabs heat to around 1,150 degrees Celsius before rolling reduces thickness. CVC crown control and laminar cooling regulate strip profile. Thickness variation stays within about 50 microns, astonishing control for metal moving at industrial scale.
Feed a 600mm diameter tube into the AR530 profile bending machine and watch heavy steel curve under controlled force. This model, built with 540mm shafts, handles thick sections up to 22mm without losing structural stability. The tube is positioned between 3 driven rolls. Gradual pressure from the upper roll forces the material downward, while the side rolls guide alignment. Controlled deformation here prevents unwanted flattening. Each pass increases curvature, tightening the radius step by step rather than forcing a single aggressive bend. Roll speed and shaft torque are adjusted according to wall thickness and material strength. The operator monitors symmetry to maintain a consistent circular profile. Too much force at once would distort the geometry, so balance matters more than brute strength. After multiple passes, the straight tube transforms into a near-perfect ring section. Wow, thick steel responding smoothly under load feels almost unreal. The AR530 proves that large diameter tube rolling depends on calculated pressure, not raw force alone. More material is removed, yet the steam turbine manufacturing process produces a stronger rotating system. Large forgings are aligned and machined to form rotor sections, removing excess material to achieve exact geometry. One misaligned cut here would throw off the entire rotation. Blades are then fitted along the rotor, each positioned to guide steam flow efficiently. Feels like every piece has a strict role or it doesn't belong at all. The rolling looks like a simple bend, but the Falcon plate rolling machine actually controls pressure step by step to shape the plate. The FACCIN rolling machine handles plates up to 120 millimeters thick and 3,000 millimeter wide, applying controlled pressure to gradually bend the material. Operators guide the plate into position, aligning it with the rollers to ensure even deformation across the width. The machine feeds the plate forward while adjusting roller positions to control curvature. Feels like the steel resists at first, then suddenly gives in all at once. That flat sheet doesn't look like it would ever curve this cleanly, yet it folds into shape under steady force. As the plate advances, repeated passes refine the curvature until the desired diameter is reached, with a minimum of 400 millimeters. The rolling continues until both ends approach alignment, forming a near-complete cylinder. The gap between the edges slowly disappears, almost like the metal is closing itself. Additional adjustments correct any deviation, ensuring the final shape meets dimensional requirements. You wouldn't expect something this rigid to respond so predictably under pressure. The FACCIN rolling machine maintains consistency through controlled force distribution, preventing uneven bending across the plate. Operators monitor alignment and curvature continuously, making small corrections to avoid distortion. Every pass adds control, not just more bending. The finished cylinder holds its form, ready for welding or further fabrication. There's something satisfying about seeing a flat plate turn into a solid curve without cutting it apart. Can aluminum really be welded in the friction stir welding process without reaching a molten state? In the friction stir welding process, a non-consumable tool is pressed into the joint line and travels along the seam, generating heat through friction while keeping the material in a solid state. No liquid phase, but the bond holds like a single piece. The material softens locally and is stirred together under pressure, forming a continuous joint with refined internal structure. Feels like the metal is being mixed rather than welded. The tool movement controls heat input and material flow, producing seams with high surface quality and strong internal bonding. This method avoids defects commonly linked to fusion welding, improving mechanical, electrical, and chemical performance.